Hi everyone, and welcome to the flipped recording for 3.08 solutions. Be sure that you're taking notes during the recording to add to your science notebook. Remember also to update that slide with the lesson number and title. So if you can see the image here, you just make sure you update that you put all the guiding questions on the right side, and that you add to your notes. I will give you note ideas as we read through the lesson. So as we jump into solutions, I know your screen might look a little bit different from mine with it being the teacher screen, but we're talking about solutions. So it's a hot day in the summertime. You look around the kitchen and reach for a pitcher of and some lemons. Yes, lemonade. After squeezing some lemon juice in the pitcher and adding water and ice, you pour a tall cold glass and take a sip. Ugh, too sour. You forgot to add the sugar. Quick, where's the sugar? You want a refreshing drink right now. So what do you need to do to get the sugar to dissolve quickly into the lemonade? You'll answer this question and explore the concept of solutions in this lesson. So we have lots of key words to define in our notes as we get started. The first is a heterogeneous mixture. It's a mixture in which different parts have different compositions, made of different proportions of particular atoms or molecules. So this could be something like Chex Mix, or something where you can see the different parts in it, a heterogeneous mixture. And then we've got a homogeneous mixture. So this is a mixture in which the ratio of each component to the other is the same everywhere in the mixture. So it looks uniform. You can't see the different parts like you could in the Chex Mix. So think about milk. Most drinks that we have are all most uniform in color. That means you can't see the other parts in there. Then the definition of mixture is a combination of two or more substances that do not change chemically when mixed together. So trail mix is an example of a mixture. You want to put that in your notes too. The example I think is helpful. And then the next three words are something that students mix up often. So it's important to find a way for your brain to remember the difference. So a solute is the minor constituent of a solution. And we'll talk more about that as we read that page. So you can put some examples down. So it's usually the solute is what you're trying to dissolve. And then the solution is a mixture in which the different types of matter cannot be easily separated. So when a solid, liquid, or gas combine or completely mixes or dissolves into a liquid, it becomes a solution. Milkshake powder stirred into milk is a solution. And then a substance is matter that has particular properties. So salt is a substance that dissolves easily in water. Okay, as we get to the next page, we've got 10 guiding questions that we need to answer in this lesson. So if I take a quick screenshot of those for us to read. And I'm going to have to keep flipping back and forth to the questions in this lesson. I am not on my same computer with two screens to look back and forth. So the first thing that we're going to look at is what are pure substances and give some examples. Okay, now we're ready to get into the content of the lesson. So pure substances. Matter can be categorized into one of two groups, pure substances and mixtures. So it might be helpful for you in your notes to kind of make maybe a little pyramid diagram showing matter at the top and then branching out into pure substances and mixtures. And then we can branch off from there. Pure substances are made of either one kind of atom or one kind of molecular compound. So H2O could be a pure substance if we're talking about, we'll give some more of those examples coming up, but it's one kind of molecule in there. So it'd be like H2. That would be a pure substance, not H2O because you have hydrogen and oxygen. We'll talk more about that. So a pure substance is composed of one kind of atom that's called an element. Pure substance. So that's composed of one kind of atom. Remember, we talked about that. If it's H2, that's one kind of atom. It's an atom of hydrogen. Pure carbon, pure gold, pure oxygen, those are all elements. Matter that is composed of more than one kind of atom, but only one type of molecule is still a pure substance. So again, water is a pure substance, even though it is made of two different types of elements, hydrogen and oxygen. These elements are bonded together in exactly the same way in each molecule of water. So that's why water is a pure substance. That H2O, it does not change. That ratio never changed. They're bonded together. So other examples of pure substances that are not elements include things like table sugar or carbon dioxide, that's CO2 that you guys have seen before. So you might want to write those examples down because they are different, especially the water being a pure substance, because your brain might go like mine does, kind of thinking straight to just an element. And we really need to make sure that we remember that it can be a molecule with a fixed ratio. So if we scroll down here, you're able to see how do you know if the gold jewelry you buy is pure gold? So the term carat is used to describe the purity of the gold, and it's based on a total of 24 parts. Pure gold is known as 24 karat gold. In 18 karat gold, for example, 18 of the 24 parts are gold, and the remaining 6 are parts of another metal, such as silver or copper. A diamond is a pure substance, and it is made only of carbon atoms. Pure gold is composed of only gold atoms. Water is a pure substance. The elements hydrogen and oxygen are bonded together in exactly the same way in each molecule of water. And then table sugar is a pure substance made of only sugar molecules composed of carbon, oxygen, and hydrogen. So hopefully those examples are helpful. And if we look at our guiding questions, what are pure substances, and give some examples, you should now be able to fill that in. So if we go on talking about heterogeneous mixtures, most of the materials we interact with every day are not pure substances. Remember that a material composed of more than one pure substance is called a mixture. Mixtures are divided into two categories. So remember I mentioned earlier having that kind of pyramid scale down, and we had pure substances on one side. You could list some of those examples, and then we have mixtures over on the other side. Well, mixtures are divided into two categories as well. So you've got mixtures can be either heterogeneous or homogeneous. So heterogeneous, like we talked about earlier, are mixtures in which the substances are not present in the same ratio throughout the mixture. For example, if you studied a piece of granite, you would see that it contains many different minerals. There might be a large piece of quartz at the top and a combination of feldspar and mica on the bottom. The ratio of the different minerals in the granite is not the same everywhere in the rock. Therefore, the rock is a heterogeneous mixture. Look at the images to see more examples of heterogeneous mixtures. So granite, if you know what that is and you're able to put this image in your head when you're reading back through your notes, that would be a good thing to have, or maybe you could take a little screenshot and have that in your notes. You can see the different pieces. Floating soap is a heterogeneous mixture that has gas dispersed in the with the solid. Dust in the air makes a heterogeneous mixture that contains particles that you can see when light is shown in the air. So that's how I can see when my kitchen floor is really dirty from the morning sunlight. But you can see that in the air. Okay, so hopefully you have some examples down of heterogeneous mixtures. And if you look at guiding question 2, it asks what is a heterogeneous mixture? You can answer that now, and then moving on to homogeneous mixture, we are ready to go back. So going on to the next slide, homogeneous mixtures. It's a mixture which homogene, so that means the same in Latin, a homogeneous mixture. The ratios of the component to the others is the same everywhere in the mixture. So in other words, the mixture is uniform. If you look at that picture of the toothpaste, even though there's different things in it, different ingredients, it's uniformly mixed. So that's how you know it is homogeneous. So for example, if you were to mix a table sugar in warm water and stir it well, you might find when you tested the mixture that the ratio of sugar to water in the top of the glass is the same as the ratio in the bottom of the glass. A glass of sugar water would therefore be a homogeneous mixture. Other examples include toothpaste, pennies, and most types of gold jewelry. So you can put some of those examples in your notes. Pennies, they look the same throughout, even though the outer appearance, they can get dirty and dirt can collect on it. It is a pure substance. They contain copper and zinc. So it's not necessarily a pure substance. I didn't mean it that way, and just that it looks uniform throughout. So most pieces of gold jewelry are homogeneous mixtures of gold along with other metals such as copper and silver. So we have a lot of jewelry examples that you can think of as well. Substances and solutions. So guiding questions, just do a quick check back. We've got 1, 2, and 3 done. Now we're looking for what are the differences between heterogeneous and homogeneous mixtures. You should be able to answer that now. Heterogeneous looks different. They're not uniform. Homogeneous looks uniform throughout. And now we are looking for colloids to be able to answer that question. So substances and solution. Most homogeneous mixtures are solutions. What do you think of when you read the word solutions? Solution. If you've worked with solutions before in your science class, you may think of mixtures involving liquids. You may be surprised to learn that there are solutions made entirely of solids and that gases mixed with each other are essentially solutions too. Can you think of some examples of solid solutions and solutions of gases? So we don't often think about a solution being a gas, like mixtures of gases. So gases can also dissolve into liquids, like whipped cream. So in some rare instances, gases can even dissolve into solids. So let's look at that. All right, so what is a colloid? This is number 5. It is a suspension, a suspension in a heterogeneous mixture from which the suspended particles eventually settle out, like dirt in water or dust in air. A colloid, however, is a heterogeneous mixture from which the suspended particles do not settle out. Hair gel, milk, soap, jelly, and mayonnaise are all colloids. Milk that is homogenized is still heterogeneous. It's just treated so the particles stay dispersed evenly. So I gave milk as an example earlier, and so it's interesting that they plug it in here that it's homogenized milk right? So that means they are doing something to it. So those particles stay dispersed evenly, even though if you've seen raw milk that has not been homogenized, the fat settles up to the top. So that is non-homogenized milk, would be a heterogeneous mixture. And then milk in general. So that one might trip you up. You want to make sure you understand that really well. Coins are solid solutions. If we look here, and whipped cream is a solution in which a gas, the air, is dissolved in a liquid. If you've ever seen like heavy whipping cream, you could pour it out of a container, but then you could use beaters and beat it, and it gets that fluffy texture that you see there in the picture. So it's got air dissolved in it. And then harmful gases can be dissolved directly into the solid charcoal in this gas mask. Okay, so going on, we got the definition of colloid, number 5. What are differences? No, that's number, 5. And now we're looking at the two components of a solution, and we're going to describe that. So that is number 6. So in a solution, any solution has at least two components. Think of our solution of warm water and table sugar. It contains two pure substances, sucrose and water. And in this solution, the water is referred to as a solvent. Okay, if we remember, solvent, that definition is a minor constituent of a solution. So it's the substance that is the greatest quantity. The solvent has the greatest quantity. So that might be something to write down in your notes as well. So there's only one solvent in a solution. So the sucrose in our solution is called the solute. And the solute is the substance that is dissolved into the other substance. Okay, so solute would be like the sugar. You may want to use that example. Sugar water, it has to be warm. And the solvent would be the water. A solute is a substance dissolved into another substance. So make sure you have that down. Our example contains only one solute, but there can be more than one solute in a solution. Now consider a solid solution, such as a gold ring. Often gold is mixed with other metals to change the properties of the gold. If you see a gold ring on the molecular level, you might see copper, silver, or even nickel atoms along with the gold. What are the properties of a substance? So if we look at this image here, properties are divided into two types. Remember, we learned this way back in Unit 2, physical and chemical properties. Physical can include color, smell, freezing point, melting point, density, and viscosity. Chemical properties can include flammability, pH level, and reactivity with oxygen or water. Okay, so you can look at the picture here. Solvent, you can see it's the liquid, the solute, the powder that's going into it. So here's a practice page to help you go through and make sure that you understand these terms and can match up with the definition. So solutes affect a solvent's properties. So let's just see where we are in our questions. We did colloids, two components of a solution. We wrote solute and solvent. Hopefully you have that in the example. So now we're on number 7. So in a solution, a solute can affect the properties of the solvent. So for example, salty water has a lower freezing point than pure water. If you've ever lived in a cold climate, in winter you may have to toss rock salt onto an icy sidewalk so it becomes safer to walk on. Why is this done? It might appear that the rough salt physically breaks up the smooth ice, but in fact the salt, which is a solute, affects the properties of water, the solvent, when the two are mixed together into a solution. What exactly happens to the ice? Water typically has a freezing point of 0 degrees Celsius. However, when salt is dissolved in water, it lowers the water's freezing point by disrupting the pattern of the water molecules as they arrange themselves to form a solid. Because salt has this effect on water's freezing point, it's often used for melting ice on sidewalks. So if you're thinking about how it can affect the properties, the solute can affect the properties. We're given the example of salt water, but salt being added to ice, the freezing point is disrupted. So you're able to give that example. It affects the properties. So that is the answer. So we're not always talking about salt water. There's other solutes and solvents that can be obviously affected as well. And so you want to just make sure you understand that it affects the properties of the solution or the solvent. All right, so how much solute can dissolve in a solvent? Imagine that you wanted to make lemonade, but you wanted it to taste really, really sweet. You could just keep adding sugar until you tasted nothing else, right? Wrong. So all solutions have limits on how much solute will dissolve in the solvent at a given temperature. In the lemonade example, at some point, the water would become saturated with sugar. If you tried to add more sugar, it would sit undissolved at the bottom of the pitcher. My kids seem to try this a lot. They put too much sugar in something like tea, and it just sinks to the bottom. So when scientists measure how much solute will dissolve into a solvent, they use the term solubility. So two words that you may not know. One, saturated. This is the definition you'll want to add to your notes. It means dissolving the greatest possible amount of a substance in a solution. Okay, so have saturated, and then solubility. It's how much solute can be dissolved in a solvent at a given temperature. Okay, so the solubility of the sugar increased when we raised the temperature. So like if you want to make sweet tea, down in Texas we drink that a lot, the tea has to be hot when the sugar is added so that it will dissolve into it. Otherwise it just settles down to the bottom. So you might think that stirring harder or increasing the surface area by crushing sugar into smaller pieces might help raise the solubility. In fact, these actions have little effect on the solubility. They can help raise the rate at which something dissolves, but once a solution becomes saturated, no amount of stirring will increase the solubility. Okay, so you could put that lemonade example in there. And then let's look at the guiding questions again. What is solubility? We just answered that. And what factors can affect the solubility of solutions? Okay, so temperature is one of those. Let's go on to the next page. So are we saturated yet? So what can you do if you want your lemonade to be extra sweet? You can raise the solubility of the solution. Factors that affect the solubility of solutions include temperature of the solvent, amount of pressure the solvent is under, and the addition of other solutes. So there are 3 things there that you need to have down to answer that guiding question. And in most cases, increasing the temperature of a liquid solvent will increase the solubility of a solid solute. For example, a solution of sugar water that is saturated at room temperature, which is 72 degrees Fahrenheit, may not be saturated at 85 degrees Fahrenheit. So to saturate the warmer solution, you would need to add more sugar. That is some sweet lemonade. To increase the solubility of a gas in a liquid, you increase the pressure. Gases are more soluble in liquids at higher pressures than at lower pressures. Pressure doesn't have much effect on the solubility of a solid in a liquid, though. Okay, so lots of confusing words here, lots of repeating words that sound very similar. So make sure in your notes that you are differentiating those things so that you have a clear understanding the difference of those words. Okay, and as we get to the last slide here, we're looking at our last guiding question. How do you interpret solubility graphs? So that's what we're looking at. Scientists often use graphs to compare and contrast the solubilities of different compounds. A solubility graph is developed by determining the amount of solute it takes to saturate a solvent at 0 degrees Celsius, shown on the y-axis. Plotting this data on a graph and then repeating the process as the temperature increases to 100 degrees Celsius, shown here on the x-axis. Once the data points are connected, the resulting graph typically shows a pattern of increasing, decreasing, or constant solubility depending on the solution. Take a look at the graph's solubility. Nope, sorry, I skipped it. Take a look at the graphs. What can you learn about the solubility of sugar based on the graph? And what can you learn about the solubility of salt? So the graph is very tiny. If we take a look up here, you're able to see the temperature as it goes from 5 to 85 degrees Celsius. And then you've got the solubility by 100 grams. So you can see the solubility of sugar, and it's increasing over time or over temperature increase. And then the solubility of salt, though, stays the same at all temperatures. So heating that solution does not do anything to the solubility of salt. So solubility graphs have also been developed to show changes in solubility due to changes in pressure and the addition of other solutes. According to the solubility chart, what is the solubility of sugar in water at 45 degrees? So if we go back to sugar at 45 degrees, it looks like it's almost in the middle of about 70. So let's look at this answer and see where we are. So the about 75. So the solubility of sugar in water is 75 grams of sugar per 100 gallons of water. I'm assuming that's gallons. All right, so we've got several things there answered. Also in that last guiding question, you're able to answer how you use those graphs. And then we're going on to the lesson review. So here, which is which, this is a little quiz to help you. Again, these words are all very similar. So just practicing and making sure you can differentiate would be really good practice. So there are 6 little questions here for you. And then checking your knowledge. In this lesson, you learned about mixtures and how to classify them. You also learned about a special kind of mixture called a solution. Answer the following question to explain solutions. So you can go through those and see if you're able to answer those or if you need to add anything to your notes. So that is a lot of information to take in this lesson. So make sure you have really good notes there so you'll have those on your quizzes and your test. Look for the flip follow-up session and let me know if you need any help.